Hello friends, welcome to my channel Biochemistry Insights. Antimicrobial resistance. Video number 4. The topic is origin of AMR. Imagine a world where even a small cut, a minor infection or a common illness could turn deadly. Sounds like a science fiction. Well, that was our reality before the discovery of antimicrobials. Antimicrobials gave humanity the power to fight deadly infections in humans, animals, and even the plants. But microbes, the invisible enemies, have been fighting back. Slowly, silently, they have evolved, giving rise to a dangerous global threat, AMR. In this video, we will uncover how resistance emerged in microbes and why understanding the origin of AMR is the first step to protecting our future lives. Antimicrobials are substances that act against microorganisms, like antifungals will kill fungi, antivirals will act against viruses, antibiotics will act against bacterial infections. AMR is a rising threat to the world. Today, AMR causes 700,000 deaths. If left unchecked, by 2050, AMR could cause 10 million deaths a year. It can even cause more deaths a year than cancer, make common infections and injuries untreatable. Antimicrobial resistance is not something that appeared overnight. It's actually part of natural system or evolutionary process that occurs over time when pathogens undergo genetic changes. Over time, pathogens like bacteria, viruses, fungi, they change, they adapt, they evolve, and sometimes they develop the ability to resist our medicines. But here's the problem. Human actions have been speeding this process up dramatically. The major causes of AMR is misuse and overuse of antimicrobial substances, like taking antibiotics for viral infections, not completing the full course of treatment, or using these medicines unnecessarily in animals, have all fueled the rapid rise and global spread of AMR. We are unknowingly helping microbes become stronger, smarter, and harder to defeat. AMR is an ancient phenomenon. Soil microbes naturally produce antibiotics and have co-evolved resistant mechanism. Long before humans discovered antibiotics like penicillin, microbes were already battling each other in nature, using natural antibiotics and evolving resistance mechanism to survive. Scientists have even found genes for antibiotic resistance in 30,000-year-old permafrost samples and ancient cave bacteria, untouched by modern medicine. This proves that AMR is a natural defense strategy used by microbes to compete in their microscopic world. So, while AMR is ancient, it's our modern misuse and overuse of antimicrobial substances that has made it a global threat and a crisis today. We are diving into a fascinating and somewhat cautionary tale, the story of penicillin, and the surprisingly swift rise of antibiotic resistance. Our story begins in 1928 with Alexander Fleming, a Scottish bacteriologist working at St. Mary's Hospital in London. As the story goes, Fleming returned from a vacation to find a petri dish contaminated with mold. But this wasn't just any mold, it was Penicillium notatum. And around the mold, something remarkable was happening. The bacteria, Staphylococcus aureus, were being killed. Penicillin's mass production and widespread use in 1940s transformed the treatment of bacteria and the infections caused by them. Diseases that were deadly, like pneumonia and sepsis, became treatable. It was a medical miracle. Almost immediately after penicillin's discovery, resistant organisms began to emerge. It's a crucial point, often overlooked. Resistance wasn't a gradual development decades later, rather, it was happening almost in real time. The first resistant bacteria to penicillin emerged shortly after its discovery. The subsequent mass production and utilization of antibiotics in 1940s. The cycle of bacterial resistance actually has three stages. The first stage is the bacteria multiplies, undergoes mutation, genetic changes. Then it adapts to the new environment. And thirdly, the bacteria develops resistance to treatments. However, resistant organisms emerged almost immediately after the discovery of penicillin. In 1942, penicillin-resistant Staphylococcus aureus was reported. In 1953, tetracycline resistance was reported. The first case of penicillin-resistant Staphylococcus aureus were reported as early as 1942, just a few years after the drug's widespread use. Think about that. The evolutionary pressure exerted by penicillin was so strong that bacteria were already evolving defenses. The problem wasn't limited to penicillin. By 1953, resistance to tetracycline, another important antibiotic, was also being documented. The writing was on the wall. Bacteria were adapting, and the golden age of antibiotics was already facing a serious challenge. This may be because widespread agricultural use of antibiotics. The widespread use of antibiotics in agriculture in the 1950s and 1960s accelerated resistance. 1961, MRSA was reported. MRSA, the methicillin-resistant Staphylococcus aureus. A global epidemic of MDR, tuberculosis, occurred in 1980s. Gram-negative pathogens such as E. coli and Klebsiella developed ESBL resistance in the 1990s. The rapid emergence of resistance highlights a fundamental principle of biology, the evolution. Bacteria reproduce quickly, and with each generation, there is a chance for mutation to occur. Some of these mutations might confer resistance to antibiotics. When antibiotics are used, they kill susceptible bacteria, leaving the resistant ones to thrive and multiply. The genetic basis for AMR evolution is intrinsic resistance. That means some bacteria naturally resist certain antibiotics due to their structure. The second phenomena can be acquired resistance. That means an organism acquires resistance via mutation or horizontal gene transfer. Horizontal gene transfer means exchange of resistance gene via plasmids, transposons and bacteriophages. The evolution of antibiotic resistance occurs in three stages. The first stage is the exposure to antibiotic itself, where bacteria encounters the antibiotics and most of the bacteria they get killed because they are susceptible, leaving behind very few ones which are resistant. Then the resistant ones multiply very fast and pass on their genes to other susceptible bacteria in a way that they also become resistant. This is natural selection in action. The more we use antibiotics, the more pressure we put on bacteria to evolve resistance. Today, we face growing crisis of antibiotic resistance. Superbugs like MRSA pose a serious threat to public health. These resistant bacteria are difficult to treat, leading to longer hospital stays, higher medical costs, and increased mortality. Multi-drug resistant organisms and superbugs. There are some high burden pathogens such as E. coli, Klebsiella, methicillin resistant Staphylococcus aureus, Pseudomonas, and Mycobacteria. These bacteria show resistance to multiple classes of antibiotics, making infections harder to treat. Zoonotic transfer of resistance is another big problem. AMR spreads between animals, humans, and the environment. The race is on to develop new antibiotics and alternative strategies to combat antibiotic resistance. But the most important thing we can do is to use antibiotics with responsibility. The quest is on for a new antibiotic innovation. Scientific research, technological advancements, and collaborative efforts all are pointing towards the discovery of new antibiotics. Use antibiotics only when necessary. Follow your doctor's instructions. Do not share antibiotics. This map speaks volumes. Antimicrobial resistance is no longer a distant threat. It's a global emergency. From North America to Asia, from Africa to Europe, resistant infections are rising fast. These superbugs are no longer confined to hospitals. They are spreading across communities, agriculture, water, and even the environment. Low and middle income countries, especially in the parts of Africa, Asia, are facing high burdens due to poor sanitation, antibiotic misuse, and lack of regulations. The impact on healthcare is equal to longer hospital stays, higher medical costs, and increased mortality. Prevention is key. Practicing good hygiene can help prevent infections in the first place, reducing the need for antimicrobials. The story of penicillin and the dawn of resistance is a powerful reminder of the constant battle between humans and the microbes. It's a battle we can't afford to lose. The drivers for global AMR is the global spread, poor infection control, lack of antimicrobials, and the overuse of antimicrobials. Global efforts to combat AMR are also being taken. World Health Organization is strengthening surveillance, stewardship, and innovation. A coordinated action, the One Health approach, is being taken to monitor the spread of AMR in human, animals, and the environment. Antibiotic stewardship program, research and innovation, public awareness and education. They are working in all these sectors. When the world stood at the brink of post-antibiotic era, global powers rose to unite. From health to trade, from environment to agriculture, these agencies are leading the global war against AMR. To defeat AMR, the world must act on 5 strong pillars: strategy, science, stewardship, innovation, and awareness, from global plans to local action. These are the shields we must raise to protect the future of medicine. At the heart of these efforts is the One Health approach. This recognizes the interconnectedness of human, animal, and environmental health. AMR doesn't respect boundaries. It spreads across these sectors. Therefore, the solution must be integrated and collaborative. The world is not standing still. From national action plans to global collaborations, from leading organizations to visionary strategies, humanity is fighting back. But the battle against AMR is far from over. The future demands vigilance, innovation, and unity. Because if we don't act today, tomorrow's infections may become untreatable. The story of AMR began long ago, but how it ends is in our hands. Thank you for watching. Learn more about AMR in our coming videos. If you enjoyed, please do not forget to like, share, and subscribe.